Professor César Fosco, if you're right. Yeah, thank you very much. So Professor César Fosco is from the Centro Atómico Bariloche from Argentina. So thank you very much for accepting our invitation to this meeting. Please go ahead, Professor.
Thank you for the invitation. I apologize in advance because I feel like an outsider regarding the condensed matter physics point of view, but I will do my best to explain what we have done in this area. So this work is part of what we have done in collaboration with a student of mine as part of his master degree thesis, Agustin Silva. And well, it has to do with something which we have studied, which is the relationship between the chiral anomaly and the vacuum polarization for a Dirac field in the presence of a defect. So as you know, chiral and other anomalies have to are relevant to both theoretical and phenomenological aspects of quantum field theory. And their origin is in ultraviolet divergences, which come from short distance fluctuations which require a regulator. And then that regulator necessarily introduces a mass scale. And there are symmetries which are sensitive to the presence of any mass, like chiral symmetry, conformal symmetry in the case of two-dimensional theories, and well, even in higher dimensional theories. So the regulator breaks the symmetry, and that breaking manifests itself even when the regulator is removed. By remove, I mean when the regulator scale tends to infinity when it's removed. So when you have such a violation, you speak of, you say that you have a quantum anomaly. So it's a quantum violation of a classical conservation law. This is what we call an anomaly. And in the case I'm going to talk about is the chiral anomaly. And in the context of having also boundary conditions, non-trivial boundary conditions, we know that boundary conditions are rather explicit, in general, can be rather explicit breaking of symmetries, not just special ones, because some boundary conditions can break, well, chiral symmetry, and in the case of supersymmetric theories, you can break supersymmetry, even with compact dimensions where you don't have any special point. And they have physical manifestations, like the Casimir effect and Casimir polder. So the presence of boundary conditions in a quantum field theory manifests itself in physical phenomena. And well, I mentioned that we have been working in for fermionic theories. So in physics, we meet many realizations of non-trivial boundary conditions for fermionic fields. One of them is in the what people call the back model of QCD. That consists, as you may know, as Dirac massless fermions in the presence of conditions which correspond to the vanishing of the normal component of the current at the boundaries. Usually they are used to model a nucleus, so this is modeled by considering, for example, a sphere where the current due to a massive Dirac field inside the sphere vanishes on the boundary, and they well, they use that to model a nucleus, and the vacuum energy, the Casimir energy of the fermions is related to, is used to match the mass of the, is considered to be part of the mass of the nucleus, for example, of a nucleon, not of a nucleus. In the context of condensed matter physics, or nanophysics, there are some carbon nanotube models where you have fermions and they Dirac fields, and they obey non-trivial boundary conditions. Well, I have some reference, some not so old references. And so there is some real physical interest in considering boundary conditions. Of course, if you have models like systems like graphene, naturally, if you have a finite sample, you will have, usually you do have borders. You don't work with the torus, for example. So it makes sense to use, to consider non-trivial boundary conditions for a Dirac field. So it is our aim is to study the interplay between the anomalies and these non-trivial boundary conditions for fermions. The system itself will be fermions in the presence of a potential which may be used to impose back boundary conditions. In order to impose, you may guess already that in order to impose a boundary condition, the potential has to be singular. So it has to be a space-dependent potential, of course. Well, it has to be, in this case, a space-dependent mass term. Well, in this reference, they prove that it has to be, you need a singular potential in order to impose back boundary conditions. And why to study that interplay? Well, there is a sort of, I don't know, maybe paradox is a rather strong, a strong name, but we were thinking about what happens in 1+1 dimensions, but if you consider a massless Dirac field, you know that the Chiral anomaly in this case in 1+1 dimensions is enough to fix the vacuum polarization tensor exactly. You know, you can integrate out the fermions in the presence of a background gauge field exactly, and that is determined by the anomaly. An equivalent way to say that, to say the same thing, is that the current due to an external abelian gauge field in 1+1 dimensions, in the absence of borders of any boundary condition, of course, the normal current is conserved, so it has its divergence is 0. On the other hand, the curl of that current is proportional to the anomaly. So you have a vector field which is a current of which you know the diversion, which is 0, and you know the curl, which is essentially the anomaly. And that is enough to fix completely the vacuum polarization tensor in 1+1 dimensions. So the paradox is if the anomaly is independent of the existence of boundaries, and at least if you are not on the boundary, say. So how is it that the vacuum polarization tensor sees the boundary? Because it must see the boundary, because of course the current has to vanish on the boundary. So in some way it has to be sensitive to the presence of boundaries, but on the other hand, it is completely determined by the anomaly. So if the anomaly doesn't change, how does that manifest itself in the vacuum polarization tensor? That was the paradox we wanted to study. So I will, in this talk, I will describe the system first. Then I will mention the evaluation of the Chiral anomaly, both for the case of back boundary conditions and for a little more general conditions, which amount to, say, to allowing part of the current to flux out of the region contained by the boundaries. Then I will evaluate the induced vacuum current in the presence of the boundary and the related vacuum polarization tensor, and then I will comment on the previous results. So the system is just the fermionic field, Dirac field, in d+1 dimensions, which in my case, d will be just 1 or 3. The Dirac fermion will be coupled to an abelian gauge field. The non-trivial boundary conditions will be at the, well, it will be a point or a line, depending on whether we are in 1 or 3 spatial dimensions, will be at, so the last spatial coordinate will be 0. And the potential will, potential between quotation marks, is something which appears as a space-dependent mass term added to the kinetic term for a Dirac field. And she is a dimensionless constant. So you see that delta function has the dimensions of a mass and has the same dimensions as the Dirac operator, so she is dimensionless. And how do you get from here back boundary conditions? Well, that's the first question. Well, this is just my conventions. I'm sorry about this. Is for us, h bar is equals 1, speed of light equals 1, and well, these are we use chiral representation for the gamma matrices. So, which is the relationship between the singular potential and the boundary conditions, which appear with back boundary conditions appear for g equals 2. I recall that the back boundary conditions correspond to the vanishing of the normal component of the current, which at the boundary, which in this case is xd equals 0. So as usual, one way to derive the boundary conditions is to integrate along a line, integrate the Dirac equation corresponding to this, along a line which encloses the point, the argument of the delta function. What you see is from the kinetic term, you get something which depends on the term which contains derivatives along the xd coordinate. This is not unusual, but regarding the singular term, you get something which depends just on psi evaluated on at the boundary at 0. You see, the only way to make sense of this is to start from an approximant of the delta function, and then you realize that you have to replace this psi evaluated at 0 by the average of two different lateral limits for psi. Rather than putting here just psi at 0, you end up with the average of psi between the two possible lateral limits approaching 0. Why? Because this kind of singularity is so strong that psi can be discontinuous across the potential. So from this equation, which comes from integrating out the Dirac equation, you can introduce projectors, this p plus minus, which are defined in this way, and setting g equals 2, the previous equation for this continuity can be written in this way, involving psi approaching the boundary from one side and psi approaching the boundary from the other. These projectors are orthogonal, so acting with any one of these projectors on this equation, you get the vanishing of the other. So both projectors acting on, well, p plus acting on psi from positive values of xd, say, has to vanish, and the same happens for p minus acting on psi approaching the boundary from below. And these linear conditions are the back boundary conditions. So they imply that the current vanishes, right? So they are back-boundary conditions are linear conditions on the field, which imply the vanishing of the current. If you have this, you have this bilinear object vanishes at the boundary. This happens for g equals 2 when g is not equal with is different from 2g. You have current flowing across the boundary between well, in this case, two regions, which corresponds to positive values of xt or negative values of xt. I just wanted to mention that there is a similar, well, actually an identical system, but with a massive Dirac field, which we had considered some years, well, many years ago. And this is used to construct something which people call overlap Dirac operator, which is a way to represent massless chiral Dirac fermions in an even number of dimensions. And well, but this corresponds to psi equals -2 the sign of the mass. So this is a way, there is a way to introduce a defect in a higher dimensional theory to generate, via the Kaplan mechanism, to generate chiral fermions sitting concentrated on the defect. But it's a different value of, it's a different sign actually for psi, and it has to be a massive fermion. I am considering here just massless fermions. So how do you calculate the anomaly? The anomaly is evaluated usually, in this case, is, well, you can relate it to the divergence of the axial current. The expectation value of the axial current is maybe introduced in terms of functional integrals in this way of defining the expectation value, of obtaining the expectation value in the presence of an external gauge field. As you know, well, in the absence of any defect, the classical result for the divergence of this current could be 0. In the presence of the defect, the equivalent of the classical result is not 0, because the defect behaves like a mass term. So you get something like this. You get the divergence of the current can be different from 0 just at the defect. So even classically. So we wanted to see what happened outside, say in the bulk of the system, not just on the defect. So as you know, in order to calculate the anomaly, you have to take care of the divergences due to the fact that you have coincident points here. So this bilinear is ill-defined because of ultraviolet divergences, and you can handle that from using many different approaches. I don't know. You can attempt to calculate the divergence by following the Fushikawa approach, or you can just evaluate the expectation values using perturbation theory. Well, one possible way to do that in the previous using perturbation theory is just to introduce a Pauli-Villars regulator field to make sense of the divergence due to the coincident points. The Pauli-Villars regulator has to be, in this case, has to be a bosonic field with the same actions as the previous field, but with the mass term, with the regulator mass term lambda. And then the divergence, the quantum divergence of the axial current is obtained by removing the regulator. So you calculate the expectation values which involve the original current and the contribution from the regulator, and you get this, and then you evaluate everything on the right hand side, and then you remove the regulator. In the absence of the defect, you get this procedure gives you the chiral anomaly. In this case, what we got was something like this. We get the classical result, which I mentioned previously, plus something which I call A, which is this, and which in the case of having chi equals 0, gives you the anomaly. For chi equals 0, this is the anomaly for in the absence of any defect, and taking advantage of the traces between Dirac matrices, you can write this in this way. This function is something which satisfies it equals 1 when x equals 0, and f and all its derivatives vanish when x goes to infinity. And so it reproduces the known results for the anomaly. And so that is when, in the absence of defect, when there is a defect, you can evaluate the anomaly, as I mentioned, by many different approaches. And when chi equals 2, you can do that using known results for the anomalous Jacobian in the presence of in manifolds with boundaries. That is just for only for chi equals 2. Which in the heat kernel method you can get the log of the Jacobian, which is essentially the quantum anomaly. In this way, you have to you have expressions for these coefficients depending on the external field. You have f mu nu and some objects which depend on the projectors. Higher order coefficients do not contribute here because the results which we applied were for curved manifolds. Here we're considering just a planar boundary, and the space-time itself we consider is flat. So we particularize this for d equals 2 and d equals 4. And for d equals 2, only one of the coefficients contributes. And what we found was that the anomaly in the bulk, say outside of the boundary, which in our case was x1 equals 0, has the usual form. So there is no quantum correction to the anomaly in 2 dimensions, and the same in 4 dimensions. So, but you have a different contribution. The contribution for 4 dimensions comes from A4. So that is just for chi equals 2, which is back boundary conditions. What happens when you don't have boundary? You don't have back boundary conditions, but something more general with where the current can actually flow out of the region you are considering. Well, you can use, for example, the perturbative approach to calculate the anomaly, and this object which appears in the evaluation of the divergence of the axial current can be separated into 2 pieces. Well, we have defined the object here, and we have checked that the first term reproduces the anomaly with corresponding to back boundary conditions. So we checked what happened with the other contribution, which depends on chi, and well, it's a rather technical proof, but we managed to show that when you are not sitting on the boundary and you take say you are shooting at the point epsilon inside the region where the fermions are confined, and you take the limit of the regulator going to infinity, the extra contribution vanishes also. So there is no no extra contribution to the anomaly. So the result for back boundary conditions is stable even for values of xi which are different from 2. The reason is that this contribution, as you may see, vanishes with when lambda goes to infinity. It only has negative powers of, well, it has negative, an overall negative power of lambda. So the only way in which it can contribute is if something makes it divergent, and the only possible origin of a diversion here is a coincidence between these two, between the points in the different objects which appear here. If you are not sitting on the boundary, that cannot happen. So what about the vacuum polarization tensor? Say the expectation value of the current. So from the point of view of the anomaly, we have seen that there is no change in the value of the anomaly, the current anomaly. So what happens with the vacuum polarization tensor? Well, you can evaluate the current, expectation value of the current in the presence of the external field and the defect. If I expand in powers of A, say in linear response theory to calculate the expectation value of the current, using treating the defect exactly and the external field up to the linear order, say, for the current, what you get using that expansion is something which has this form. So J is of course linear with A, and here you have this object, which is the vacuum polarization tensor in the presence of a defect. So it depends on the fermion propagator SF of XY, which is the Dirac field propagator in the presence of a defect. So it has the same structure as the vacuum polarization tensor in free space, but the propagator here is in the presence of a defect. So to proceed, we need the explicit form of this propagator. So of course the system, in spite of the fact that you have a defect, the system is invariant under time translations, so it can only depend on the difference between the time arguments. So you can actually Fourier transform in time, and we leave the spatial coordinates untransformed. So the vacuum polarization tensor will depend on frequency and on the two, in 1+1 dimensions, on in principle the two spatial coordinates S1 and Y1. So this is the vacuum polarization tensor in terms of the fermion propagator. The fermion propagator in Fourier space, so Fourier transforming with respect to time only, can be found explicitly in this way. So this is the, it can be written in terms of the, well, this is the free propagator. Free means here not just in the absence of any gauge field, but also in the absence of the defect. So as you see, this expression depends only on the free fermion propagator and gives you the propagator for in the presence of the defect. So this is the propagator in the presence of the defect. In this mixed Fourier representation, you have to insert this into the vacuum polarization tensor. And when you do that, well, this is a technical point. Of course, it has to do with Lorentz invariance. When you have the correlator of two currents, as the vacuum polarization is, you work in a non-covariant way, because I am non-explicitly covariant way, because Fourier transform is just one of the coordinates, one of the arguments, the time. You may actually find out that you miss a contribution which is local in space and time, which is called the Siegel term. Well, this technical point. If someone is interested in this, we can discuss it later. So we inserted the value of we inserted the Fermi propagator into the expression for pi mu nu, and the result, you may see that here that the result for the propagator depends on this is the sine function sigma. So it depends on whether you are whether the arguments are inside the region limited by the defect or outside. So the defect is x1 equals 0. So in principle, when you insert this into the expression for the propagator, you have to distinguish whether you are the arguments are both inside the region of inside the region limited by the defect, or one of them is inside and the other outside. So when both arguments are inside the region, the result may be written in this way, which is rather explicit. When one of the arguments is, say, inside the region and the other outside, which corresponds, for example, to this, you get this expression, where you may see explicitly that if G equals 2, this vanishes. So this means, of course, that the induced current due to for example, to an electric field which is outside of the region limited by the defect, will be 0. So this is what back boundary conditions should do. So it is like an indirect verification of the fact that G equals 2 imposes back boundary conditions. Sorry, is someone talking here? So the form of vacuum polarization, well, say when G is different from 2, you have a contribution, but the form, say the induced current, will be rather similar to the one you have for free fermions, say in the absence of a defect, but say this factor is smaller than 1, so there is a suppression factor. So you have in general, we have a smaller current when you act on the fermions from an electric field from outside of the region they are supposed to be concentrated on. I'm sorry, I will not talk about the Siegel term, which is this contribution here. You can check explicitly that the vacuum polarization tensor you obtain is conserved, so it's transverse, which in this mixed Fourier representation is what appears here in equation 11. So the same can be, the same kind of calculation can be implemented also in the case of 3+1 dimensions. Here, well, I recall that the defect will correspond here to x3, to the x3 equals 0 region. So you will have invariance not only under time translations, but also translations along the plane x3 equals 0. So you just Fourier transform with respect to those three coordinates, time and the two coordinates on the plane. And you can evaluate also the explicitly the vacuum polarization tensor in this case. There are some differences in the, well, you may say that this is the generalization of the previous case. The only difference is that you, rather than having the sign of the momentum here, you will have the unit vector defined in this way in the space of the three momenta which you use to Fourier transform. And well, the vacuum polarization tensor can be written as in 1+1 dimensions. You can write it in a rather compact form in terms of the vacuum polarization tensor in the absence of defects in this way. So you have this contribution plus something which looks like a reflected contribution. So it appears as a contribution of a free term plus an image contribution. This can be interpreted as, well, it's a rather simple interpretation that in 1+1 dimensions, you can decompose the current as the sum using the Helmholtz decomposition as the gradient of a scalar plus the curl of a pseudoscalar, and the Laplacian of the pseudoscalar part is determined by the anomaly. This is because when you take the curl of J mu, this is actually the divergence of the axial current. So this determines this pseudoscalar field here. And well, this part can be actually, as the current is conserved and the Laplacian of phi is identically 0, usually this term can be erased. And so the general solution for this pseudoscalar is that you can write it as something which satisfies the Laplace equation plus something which is determined by the anomaly. In the absence of boundary conditions, this is all you have would be, say, this linear part, and you can forget about the harmonic contribution for G equals 0, say. When you have a boundary for G equals 2, you can interpret this contribution, the contribution which actually we found, which is the image contribution, as a solution of the Laplace equation when you have a boundary, as you do in electrostatics, which can be used to impose the boundary conditions on the, well, in electrostatic would be the scalar field. In this case, it would be the normal component of the current. So you may say that this contribution, when you evaluate which corresponds to the image part here, well, it will not be anomalous in the region, in the bulk of the region contained by the defect, but it may be interpreted as corresponding to an anomaly which is outside of the region contained by the defect. So this is the main conclusion. You have the anomaly is not changed, but in order to satisfy the boundary condition, you get an extra piece in the expectation value of the current, which may be interpreted as having an anomaly, but outside of the bounded region. By the way, I mentioned that something similar can be done for the we have done for the case of fermions in 2+1 dimensions. I'm not talking about fermions in massive fermions in 2+1 dimensions. You can also do that, of course, and you will get the Chern-Simons field theory. But for massless fermions, without any explicit breaking of parity, if you put a boundary, like using the same technique as here, the boundary in principle will break parity symmetry, and you can evaluate the induced current. We have done that in a previous paper. Contrary to what happens in the Chern-Simons theory, which, as I mentioned, corresponds to massive fermions, the induced current for the case of a massless Dirac field of course will be present on the boundary, but it will. Sorry. Sorry. It will be present on the boundary, but it will be non-vanishing also in a region which is in the bulk. So I will just mention my conclusions. So we calculated the anomaly in the presence of a planar defect, which can be used to impose boundary conditions, which correspond to the vanishing of the normal current. So the so-called back boundary conditions. But well, the anomaly is outside of the defect. Anomaly is the same regardless of the value of the coupling constant G, coupling constant to the defect. So the current anomaly is the same as when no defect is present, and this has important consequences in 1+1 dimensions because the curve of the current is fixed, and the divergence is 0 because the current is conserved regardless of the presence of any anomaly. So as we mentioned, that almost determines the way in which you can impose in this case, not in 3+1 dimensions, but in 1+1 dimension, is actually you can use this analogy with images to do the same in a region with more than one defect. So the combination of these two ingredients, invariance of the anomaly plus the form of the boundary conditions, completely determine the form of the back polarization tensor. That's the main conclusion of this work. So that would be all.
So thank you very much, Professor César Fosco, for this interesting talk. So we have time for some questions. Please, Professor Urrutia, go ahead. You're mute.
Yeah, well, I would like to thank César for this very nice talk. And I just want to make a comment that a similar situation motivated the talk that Andres gave last Tuesday. You have a problem that, for example, this idea can be used for tilted and anisotropic Weyl semimetals. in which the tilting and the anisotropy is described by some Lorentz violating terms in the fermionic action, but the anomaly is insensitive to this fermionic term, the same as here is insensitive to the boundary condition.
Right.
Nevertheless, you expect that this term will contribute to the effective action of the system, because a tilted YSM metal is different from a non-tilted and isotropic. So in this sense, happens a very similar situation in a particular case of some material that is for interest in condensed matter.
Right.
So it's very nice that the same idea and motivation was done for this work previously shown before.
Right. So in a way, the anomaly is useful in the sense that it is one of the two legs of the Helmholtz theorem, which says that you can fix completely a vector field knowing its divergence and the curl, but that is in 3 dimensions. Well, we also know, if you also know the boundary conditions, of course. So the anomaly is one of the legs, and in the sense is in that sense is very useful. And the boundary conditions in some cases will give you the other parts that you need to fix completely the object.
Yeah. I just want another question. Have you written your result in terms of defective action? That, for example, in our case, the effective action was just the Pontryagin density times a theta factor that included all the effect that the anomaly doesn't see.
But well, in this case, the effective action would be just just quadratic in A and with pi mu nu between the two A's. So the effective action, you say without integrating the gauge field.
Yeah, but it reproduced the anomaly as a factor at least. Or no, I mean, not the anomaly, I'm sorry, the Pontryagin density, let's say.
Right. Well, yes, you get the anomalous Jacobian is exactly the same as in the case of no defect.
Okay. Well, thank you very much. Yes, okay. Thank you, César.
We cannot calculate exactly the anomaly on the, well, it wouldn't be an anomaly, but the expectation value of the current exactly on at the defect. That has contributions which are classical, say, plus contributions which are anomalous.
Okay, so, thanks a lot.
So any other question? So it's just a comment. Also, so when we integrate out fermions, I mean, it's clear that in order to see or to envisage applications to condensed matter, we need to introduce the chemical potential. So,
yes.
So you're working at 0 temperature and vanishing chemical potential here, right?
Yes, we have. So, yes, we have done calculations also at finite temperature, and not this kind of calculation and finite chemical potential. Usually, final chemical potential is different, but final temperature, you know, the anomaly is also insensitive to temperature.
Yeah, right. Maybe you have to use thermal field theory, right?
Sorry?
So maybe you have to use thermal field theory to compute anomaly, right?
The way is, yes, to calculate the
effect.
The anomaly final temperature is using the much better formulation where you may say that the time is compactified. And so it's basically calculating the anomaly in a cylindrical space-time. And that is the same as in the case of, say, of a planar space-time. So there is no dependence on on beta, say on 1 over Boltzmann constant times the temperature. So that can be interpreted in a rather physical way, because the fact that the time is a compact dimension in Matsubara formulation. So you have time is a compactified coordinate, will not affect the anomaly, because the anomaly is something which happens when you have 2 points which are very close to each other. So if you have two space-time points which are very close to each other, you don't see the fact that the space-time is compact.
Yeah.
When you're close enough, you can forget about the fact that there is a finite compactification radius.
Yeah, also, an interesting point to compare your results is to compute also this response within semi-classical regime, for example. So in order to compare with your results, right?
Yes.
Yeah.
I know some people have done. I'm sorry, I am a bit worried to mention this, because I am not an expert in condensed matter, not even close to an expert, but I know some people have calculated the effective actions in this kind of system with finite chemical potential, and found this. Well, this of course, these Friedel oscillations, and that
Okay.
the chemical potential introduces a scale, and then you have Friedel oscillations which with the momentum which is related to the scale set up by the chemical potential.
Yeah. Okay. So thank you. So any other question? So I think we have time. Okay. So we don't have more questions. We thank again to Professor César Fosco for this interesting talk. So and we'll go